normal volume. Okay, good. So I'm Shamridhi, and thanks Sanjib and Abhishek for this lecture. So I will be discussing sort of certain aspects of turbulence which JKB brought out over the last 6 lectures. In particular, I made some notes about what JKB was telling you all yesterday and today, and I would like to sort of connect, go over briefly some of those aspects and just to sort of re-emphasize certain salient points of what was being said. And also it's after lunch, so it probably would be a good idea to at least fix some ideas, even if you know, the ones which have been rigorously worked out on the board by JKB. The other thing is, in case any of you would, you know, have questions or queries, so I'll be sort of sitting through the some of the lectures next week as well. But otherwise, so that's my email address and that's my phone number. So in case y'all would y'all like some clarification, don't hesitate to call me. Okay, sorry. Sort of, not early morning, which is defined up to 9 a.m. or 9:30. Okay, fine. So, where did we finish, or what's been said in the last few lectures? So, one of the unambiguous sort of statements that we can make is that we are dealing with an equation of this form. I'll just set density to be equal to 1. And as we saw in the last lecture, sometimes, you know, it's important often to have a forcing with a certain given statistics that helps in certain formal manipulations. I should point out here that the interesting thing is, if you look at typical experiments in fluid turbulence, at least the ones which were, you know, greatly in vogue in the 60s, 70s, still sort of very recent experiments on swirling flows, etc., became very well developed, is that people often actually looked in the scenario where F is equal to 0. So essentially, if you have a wind tunnel, and wind tunnel experiments were very popular post-war because a lot of the wind tunnels which were developed for other reasons, became available to physicists. You were essentially driving a fluid, typically a gas. Nowadays, I think SF6 is the most popular one for environmental reasons. You drive a gas or a fluid past a grid, so there's a big fan spinning around behind the grid, and you let the flow go past the grid. The grid plays a crucial role. I don't think I'll discuss that here, but so essentially the driving is not constant. What you do is, once you force your fluid through this grid, you take measurements downstream. So there is really no role of forcing, and that's what's known as decaying turbulence. I will come back to this sector in a bit, except just to tell you that some of the problems that physicists are, or some of the solutions that physicists are after, the distribution functions, the moments, let's say, those, there is some level of optimism that those exponents should be sort of universal, whether the turbulence is decaying or in a stationary state. So that sort of goes by the, in the literature, the jargon of strong universality. So that's one sort of quick this thing. So in what I will do, since I won't be using too many formal manipulations, the forcing, you know, you can sort of worry less about. The other thing that we sort of learned in the last few lectures was that nonlinearity is crucial, and nonlinearity makes life rather hard. And the last bit of information for this equation that has come up frequently is the case of the large Reynolds number limit. So in natural settings, if you're looking at atmospheric circulation or interstellar medium, etc., you are typically in the very large Reynolds number limit. And that's sort of well mimicked by experiments of today. And the word numerical simulations hasn't been mentioned so often, but I will, towards the end of this sort of 1.5 hours, I'll try to bring that up. And so in numerical simulations as well, the issue of large Reynolds number limit crops up frequently. Okay, good. So, so here we are in a sort of puzzling kind of a scenario where we are trying to describe a phenomena for which there is no explicit definition. So we are essentially looking at solutions of the Navier-Stokes equation when viscosity is very small, or experimental results performed when the combination of viscosity, some relevant length scale, some relevant velocity, the Reynolds number. We are trying to understand what happens when the Reynolds number is large, and we call this situation a turbulent situation. However, it must be borne in mind, so just to re-emphasize, that there is no, as such, there is no formal definition of turbulence. So, one would like to discuss, talk about a critical Reynolds number or sort of crossover or transition, but there really isn't a very strict definition. So before I proceed further, I thought maybe, so how would you know if a flow is turbulent? That's a sort of vexing question whose answer lies, so all right, so we can take the Reynolds number going to infinity limit, very good. What does that gain us? Because we are always in a finite Reynolds number situation. Let's not worry about Euler flows right now. We are in a finite Reynolds number situation. So how do I know that my flow is turbulent? In the absence of a precise definition, there are certain reasonably complementary ideas to this, to answer this question. One of the ideas has to do with the idea of scales. So if you remember, what was the, so I will go through this picture once more carefully. But roughly, what was the idea? The idea was that in a flow with a very high Reynolds number, you have a certain large scale where there's an energy injection, or in case of wind tunnel experiments, that's where all the energy was to begin with. You have a very small length scale where molecular viscosity becomes very effective and energy is lost in the form of heat, for example. And there's a sort of whole range of intermediate scales over which certain things happen, which one hopes are universal. All right. How would you identify a turbulent flow? So as I said, there is no sort of precise definition for it. But one of the things which strikes you if you've sort of gone through a lot of pictures, and there's a very good book by Van Dyke, which sort of is a very old book. It sort of is turbulence in pictures. What you certainly see in a turbulent flow when you're looking at a picture is that somehow there are structures at various scales. So, for example, if you turn on your tap, I'm sort of stretching the limits of credulity, but let's do it nevertheless. If you turn on your tap and you see a nice sort of flowing stream of water, and then when you turn on the tap and make the velocity larger and larger, eventually things start appearing wiggly, and you see sort of structures at various scales, whereas previously you were seeing just a column of flow. So that's the mental picture one has of turbulent flows. It's sort of intuitive. However, it does bring out the notion of scales, and that's a sort of critical notion in this business, the idea that it's a sort of multi-scale process. Okay, so how would we describe it? So this is sort of just going over what was done. I'll just take another 5 minutes. So I sort of made some notes of what were the salient points that came up in the discussions. So the first thing is that, the flow field is sort of random, it's sort of disorganized, and that immediately suggests that a statistical description of such a flow might be a useful way to go about. So you should bear in mind that what we are going to do is sort of a physicist's view of turbulence, mathematicians and engineers have a very different view, and at the end of the class, we could suggest some texts which have a nice way of presenting them. Okay, and then it emerged just before we broke for lunch, two interesting aspects of this equation in 3 dimensions. So I'll sort of stick to 3-dimensional turbulence. If when I come to the end about shell models, etc., I'll sort of try to make some connection with 2D turbulence as well. So the first remark is, when one looks at this equation as a physicist, it's very tempting to say, okay, so you can multiply both sides of this equation as was done in class by U, so you get an energy budget. And eventually you sort of, you have an expression where the total time rate of change of the kinetic energy, once you take a dot product with U everywhere, the total time rate of change of the kinetic energy is a negative number. The dissipation rate, or often, to be very correct, it's a mean dissipation rate. So the dissipation of energy per unit mass. Now, the dissipation has the viscosity sitting outside. So it's very tempting to say that in the limit of infinite Reynolds number, or when the viscosity goes to 0, epsilon, or the mean energy dissipation rate, should go to 0. That's a sort of, something which stays you, from the board. However, as was discussed just at the break, one of the rather interesting features of this equation is that when viscosity goes to 0, epsilon the mean energy goes to epsilon 0 is the term there, okay. That's for large scale, so that's also a bad notation. So the mean dissipation rate goes to a constant. This is what JKB was alluding to as the dissipative anomaly. Just as an aside, for reasons which are reasonably well understood, it doesn't hold for the 2-dimensional case. So this is a rather striking result. How did we come to this result? So of course, one of the nice sort of experiments which were done, and I'm not sure whether the result was there prior to the experimental results, this I'm not completely sure, was that when people started measuring the mean dissipation rate in wind tunnel experiments, let's say, and they kept changing the Reynolds number and cranked it up as far as they could, they would see that the mean dissipation rate sort of remained the same after a point. It really did not vary with Reynolds number. And when computers became more and more useful and powerful, this result was borne out. The underlying reason for this dissipative anomaly has to do with roughly the fact that the velocity gradients at small scales are sort of unbounded, but let's not get there. We are interested in the physical problem. The physical problem, 3D turbulence, even if you forget everything else from over the next 1 hour, what you should remember is A, as viscosity goes to 0, the mean dissipation rate approaches a constant. And that's a really critical and rather curious result. The second result is taking off from where JKB left. So what was within the Kolmogorov picture, which is one of the first sort of nice pictures to understand what's happening in to the velocity field in the Navier-Stokes equation, one of the things which emerged was that delta V, which was the velocity difference, so I really need, okay, you can project it and make it a thing, that's not really essential. This scales as 1/3 the power of the separation. So you take 2 points in your flow, you calculate the velocity at every point, take the difference. If you're very pedantic, then you would probably take the projection of this difference velocity vector along the distance vector which connects these 2 points, and you would come up with a scaling argument which goes as r to the power 1/3. All right. So this was one of the key results of Kolmogorov theory, that that the velocity difference scales as distance to the power 1/3, as a result of which, if I define this quantity I'll just explain in a second what I'm doing. So a result of the scaling argument, which is essentially dimensional due to Kolmogorov in 1941, what emerges is, what are we after? What we are after essentially is to have a statistical description of the turbulent flow. For example, if I could calculate or measure clearly the probability distribution function of these velocity increments, and if I had a theory or an understanding of it, I should be, that sort of, that is that, and end of story. However, I can't do that. It's very difficult to actually, A, measure the probability distribution functions in an experiment or numerical simulations with a lot of accuracy, and B, theoretically, it's sort of it's sort of impossible till date. Failing which, what I would like to measure are the moments of these guys. So for example, if I could tell you all the exponents for all higher order moments for delta V, from there I would be able to reconstruct my distribution functions, if those moments exist. So what Kolmogorov theory taught us, and that's where we sort of stopped, is that the velocity difference across a scale r scales as r 1/3. From there, one can calculate the moments of these velocity difference. One can look at its scaling exponent, and the scaling exponent should go as p over 3. So it should be a linear scaling exponent. As a corollary, if one measures the energy spectrum in such a flow, then the energy spectrum should have a scaling of k minus 5/3. All of this is with the caveat that you are doing your measurements in across a scale which is certainly larger than the dissipative scale in your problem, and sort of smaller than your large scale in the problem. And this is where the physics is hoped to be universal, and sort of variety of experiments in numerics does sort of give credence to this claim. So this is the dissipative scale, and that's the large scale, and somewhere there's a range of intermediate scales over which these results a la Kolmogorov should hold. When one started actually measuring these exponents, there was a surprise. And that will bring me to the sort of the second thing that I want all of you all to remember, even if you don't remember anything else. So what does this mean? This means that if I were to do an experiment, and at the risk of annoying everyone, I would use the word experiment and numerical simulations interchangeably. So if I were to do an experiment and measure the different moments of the velocity structure function, after all, I'm after the distribution function, and for that I need a good measurement of these exponents. Kolmogorov theory tells me that these exponents should be on a straight line, which is p by 3. The reason I point out what's this specially p equal to 3 is because in the previous lecture you saw that there's an exact result The only exact result in fluid turbulence, not surprisingly, is that the third order structure function, a form of the third order structure function to be very explicit, is equal to minus 4/5 epsilon r. So the third order structure function exponent, when you put p equal to 3 here, the fact that it is equal to 1 for a certain third order combination of these delta v's is an exact result. Very good. What happens when you do an experiment? What happens is, so with white I'm drawing, you get 0 here. Then you see that these numbers, well, it's probably not as exaggerated as this, but these numbers are off within statistical errors from the p/3 prediction. So something is certainly going wrong with the Kolmogorov picture. And that's what we are going to discuss, what's going wrong. And to the best of our knowledge, so right now there are sort of reasonably believable results, I would say up to p equal to 6, 7, 8, maybe not more, where you do see this trend. So what you see is that these exponents, instead of being a simple linear function in p, it's actually a nonlinear convex function. And it's monotonic. So, as an exercise, you could go back and sort of look up exactly why it should be a monotonic increasing function of p, where you can use certain Hurd inequalities, etc., to actually show that. I will try to show that, but I'm not sure whether I'll succeed in one case. Okay, very good. So what's the situation now? What has changed after lunch? What has changed after lunch is that we are slowly skeptical. This has not changed. However, we are starting to become a bit skeptical about the Kolmogorov picture and whether the fact that the scaling of 1/3, which translates to p/3, actually holds good or not. So let's try to understand where this can come from. And in the business, this feature where zeta p is not equal to p/3 is attributed to something called intermittency, which I will try to sort of quantify a little later. When you think about the word intermittency and sort of you're worried about what it means, in this context, it just means what you think it means in English. So, and we will see why it means what it means. Okay, very good. So, all right, so we've measured this guy, and we found that Kolmogorov is off. Kolmogorov was wrong, and we attribute it to intermittency, which is that somehow the signal, a turbulent flow, is sort of quiescent sometimes, sometimes violent. It's sort of a moody kind of an object. Where does intermittency come from? Is there any other possible signature of intermittency? So I will sort of, I will sort of, that watch is right? So I will sort of try to motivate it a little using experimental results. And at the end of this lecture, I'll give you at least the ones that I remember, the right sort of references. All right, another object. Let's look at the behavior of another thing. You could do it from the second order structure function, or you could sort of measure things in frequency space. So there's, in the actual measurement, there's a little more massaging which goes in, which we can talk a little later, because you're using one probe and how you convert time scales to length scales, etc., using a mean flow kind of argument, which Jacob was discussing. Okay, good. So let's look at this quantity epsilon, which is the dissipation rate. In our experiment, I would like to measure this. So all that was sort of discussed today and the last couple of days might give you a feeling that this epsilon is a nice constant, and that if one were to measure a time series of epsilon in a stationary state, this epsilon would be nice, well-behaved, and a sort of something like a straight line. That's very far from the truth. When people started measuring the energy dissipation rate, it's nowadays on the computer, it's very easy to do. What one found was that there were periods where it was very spiky and with large values, and there were periods when, the values were much smaller. And then again, you had some spikes, okay, so what is this? So this is a strange signal. It's sort of intermittent, which again strikes at sort of, at some level, the core of the Kolmogorov argument, that when you go ahead and actually measure the dissipation rate as a function of time, you find it very spiky and not smooth. Again, you see a manifestation of the intermittency effect. So this seems to be ubiquitous. There is a difference between these two intermittencies, but first, I would, for the first another 5 minutes or so, I would like you to sort of fix certain mental images about what's happening in the flow before things become this thing. So, okay, so we already have two measurements which are sort of contrary to what we know about the Navier-Stokes equation. One, you measure the scaling exponents, and you find them in contradiction with Kolmogorov and simple sort of dimensional analysis, which seem to be very nice. And B, when you measure something like the energy dissipation rate, you find it to be a wildly fluctuating object. So where does all this come from? And the velocity field sort of begins to look like a Brownian motion. So it's sort of jagged, but it's certainly, the velocity field is intermittent, of course, but it shows up much more clearly in the dissipation rate because of what's known as sort of intermittency in the far dissipation range, which is what I'll comment on. So, okay, let's try and see what a velocity field would look like and how can we sort of measure intermittency. Okay, so the question, I'll keep this diagram. So the question that Abhishek was asking was, what happens if you look at the velocity field? Why do you want to take the trouble of actually going ahead and looking at the dissipation rate when you can just measure the velocity? Okay, good. So let's see what happens. So this is the sort of cartoon that we have in mind about the velocity field, which 3 days ago we were looking at on the board. Is this field self-similar? That's the question. So if I because that's at the heart of the Kolmogorov picture. If I look at this velocity field and zoom into any section with a reasonably large, a window which is not infinitely small, but of a finite width, I would have a picture which is not too dissimilar from the one you have visually. Okay, good. Suppose, just as a thought experiment, actually this sort of signals do come across in problems of sort of mass distribution on fractal sets, etc. Suppose I had something which was like a signal which was like this. In this case, depending on where I zoom in, this curve does not appear to be self-similar. Let me recast this. Imagine this is something like a Brownian motion, right? So it has a Wrigley signal. What I'm after is my signal self-similar? So, or in other words, if I take a finite window and if I'm looking at that signal on magnification, is the signal qualitatively being reproduced or not? Okay? In the first case, modulo my drawing skills, if one were to put a window here and then slide it here, slide it somewhere else, you would typically, within this window, you would typically magnify a signal which sort of roughly looks like the original signal. Okay? So for the Brownian case, it's sort of easy to see. However, if your signal was something like this, so what I was trying to replicate is a rather interesting function which actually comes up in problems such as the Burger's equation, which is known as a devil's staircase, where you have regions which are flat, and then you have sort of steps. Okay? In this case, depending on whether I zoom in this region, or let's say I zoom in this region, I would get a very different zoomed signal. This would give me something which is flat, and this would give me something which is at least rising. Abhishek, we can, is it? No, I'll come to that statement later. What I was trying to show first, it will show intermittent. What I was trying to show first is qualitatively an intermittent signal and a signal which is non-intermittent can be in a very cartoon way sort of highlighted by these two things. And then let's see how you quantify this, this object. Okay, fine. So how would one like to quantify what's happening? So one could do what one typically does is, in statistics, what one typically does for these kind of things is measure what's known as a flatness of the signal. So let me first define or come to the definitions, and then we can qualitatively see what it means. It's the following. Okay. So suppose I'm interested in that signal, a signal which is given by V of t. So a few lectures ago, we saw that one of the nice ways to actually treat this signal is looking at its Fourier transform, right? This and this? Yeah, so, okay. The difference I'm trying to highlight is the following. It's still qualitative. Huh? I'll give you an example a little more concrete later. This signal is sort of self-similar. What it means is, I mean, I should have been a bit more wiggly about it. What it means is if I were to magnify any finite portion of the signal in this time window and slide the window somewhere else, within that window I would see a signal which sort of roughly looks like my full signal. Okay? However, if I have a signal which there are points when that signal does nothing, and there are points when that signal sort of varies a lot, then depending on which region I magnify, I see something very different. Okay? So that's the point I'm trying to highlight, and then we'll see how one can, do it better. Okay. So one can always look at the Fourier series of this signal, okay? And now I want to measure this object. So what I want to do is I want to take a high-pass filter so that I retain only the large frequencies of the sky. Right? So this is a filtered signal. And then I would like to measure a quantity, a non-dimensional quantity, which in statistics it's the flatness, which is the ratio of the fourth order moment divided by the second order moment squared after filtering. The question is this quantity constant with omega? So depending on where I provide the cutoff, does this quantity vary or does this change with omega? And this is a very useful sort of trick to work with, for any process that need not be turbulent. Now the question is that for functions or signals which are intermittent, so which have an on-off kind of situation, then this guy sort of grows in an unbounded manner as capital omega becomes larger and larger. What you could certainly do as a sort of exercise is take the signal to be Gaussian and find out what f omega is and whether it actually grows with capital omega or not, or whether it approaches a constant as omega becomes larger and larger. Okay, what does this have to do with turbulence? So that was the original question which brought us here, is whether velocity signals themselves are intermittent or not. Now it turns out that from a lot of experiments which have been done, and this is more from experiments than numerical simulations to the best of my knowledge, real experiments, is that this velocity field is not as self-similar as one had hoped it to be when constructing Kolmogorov-like ideas. So the velocity field itself, I mean, one doesn't even have to go to the dissipation rate, shows signs of strong intermittency, okay? However, that still doesn't address the Kolmogorov issue. That's because I'm measuring the flatness where the frequency is going to infinity. So what I'm really looking at are small-scale structures. And Kolmogorov is typically not concerned with small-scale structures. Kolmogorov is typically concerned with intermediate asymptotics. There's a way to bridge this story. So, okay, so at the risk of having confused everyone, let me sort of reiterate the essential point. The essential point is that in a turbulent flow, the velocity signals are certainly intermittent. They are not really self-similar, and we'll now sort of derive a reasonably simple model where this can show up. Okay, so, sorry? Let's look at a perfect, my drawing skills are. So what I'm trying to draw, which you could draw in your exercise book much better than I would, is sort of a wiggly self-similar signal, all right? Now play the following game. Take a switch and make this signal, so this is a V of t, okay, right? By hand, make this signal off for a fraction gamma of the total time that you have. So you have a signal as a function of time. Use a filter such that the signal is off for a fraction gamma. Okay? So then if you calculate the flatness, you would see, for example, it will grow as 1 over gamma. So that's a quick way to actually calculate this. After all, if you have this filter, then V gamma fourth would just grow like, and because you put the gamma in there. Okay, fine. Kolmogorov picture that we had in mind, or the so-called cascade picture. What we had in mind were these. So thankfully, JQB introduced the word eddy, so I don't have to stumble and stutter trying to make it any more precise than it deserves to be. So the picture is that you have these big blobs containing energy. So for example, if there's a circulation or a stirring in your flow, then it's sort of typically of the size of that stirring. What we know is that you have a certain energy injection epsilon at the largest scale of your problem. Let's call it L naught. I think that was the convention. You also have at very small scales things which dissipate with the rate, again, epsilon. These are at scales of eta, the Kolmogorov length scale, which was discussed in class. And the whole idea was that there's a range of scales given by those R's where these energy-containing eddies sort of break up into smaller and smaller ones. And this epsilon just flows through them. So there's an energy flux going through a certain length scale, L. Okay, what is this picture? So, so yesterday, this was this idea which was brought out by saying there's a capital L large scale from where energy gets transferred to a small scale, small L, where viscosity kicks in, energy injection here, energy dissipation here. In these intermediate range of scales, there's a constant flux of energy. Very good. The mental picture of this cascade that one associates, and it's sort of historically, it's quite interesting that this picture predates Kolmogorov. Although you probably wasn't aware of this, this was in the 1920s. The picture was that you have these big blobs of energy containing. They break up into smaller and smaller blobs, or daughter eddies, if you want to be very creative about it. And then eventually these break up small enough for grad squared U to become reasonably important and dissipation to happen. That's the sort of hand-waving picture in which Kolmogorov fits. And you can talk about, so I'll just fix the notation so that I'm not, okay, so this was the notation that was used, L0, and then at each generation, you're talking about number of blobs which are created, whose whose size is RL0. And the next generation, R squared L0. So essentially, you're talking about eddies, which, as the energy cascade happens, breaks up into smaller and smaller parcels of energy-carrying fluid, whose sizes go down like this. Okay, how would I incorporate? Okay, so this picture is consistent with Kolmogorov's simple scaling argument. Now, I just told you that this exponent is not quite correct. Can I massage this picture and recover a scaling exponent which is different from p by 3? That's the whole idea. Is there a self-consistent theoretical way to understand cascades which also has ingredients of corrections to Kolmogorov scaling? So the question is reasonably clear, okay? Good. Yes? You supply energy at some big scale, and you know that you have to drain out energy at small scale. How do you go from that big scale to that small scale? And one of the sort of appealing pictures intuitively would be that these large scales start cracking up and making smaller and smaller scales through which energy eventually breaks into. No. So you remember the Fourier transform that Jacobi was showing? You don't get peaks at certain different scales. I mean, what you essentially get is something like a k minus 5/3 over an intermediate range of scales. So, of course, what is a bit non-trivial, since you raised this point, what is a bit non-trivial? So in all of this, I'm assuming that I've hit fully developed turbulence, that I'm statistically homogeneous and isotropic, because, well, I can say that I really don't care how I got there, but sort of a truthful answer is I really don't know how I got there. So there are sort of a whole series of instabilities and bifurcations which has led me there. Once I'm there, this is the picture I'm trying to construct to try to see how much of experimental data and observational data I can explain. And so I'm trying to begin at the simplest possible picture. And there's a rationale why this picture is very popular, which has to do with fractals and stuff, but yeah. Okay, yeah. So, which is the following, that part of this picture, thanks Abhishek, part of this picture sort of gives rise to this picture in Fourier space. And I'll try to explain what each segment of this curve means using exactly these ideas. That when you measure the energy spectrum, you get over an intermediate scale the celebrated Kolmogorov 5/3 scaling. Then there's an exponential decay. That's very interesting why it's exponential. And at the small k, things are not universal, and depending on whether you force it in a washing machine or a wind tunnel or what have you, you get slightly different structures. Okay, so this is the picture which is sort of consistent with the Kolmogorov idea. Why is it consistent? One of the things that this picture retains is a certain level of scale invariance and the idea of cascade. Now, what I'm after is I want to make my signal intermittent. Okay? And then, having made that, I want to see, can I get an exponent different from p over 3? One way to make this signal intermittent, or one way to modify this cascade picture, was an early attempt made in the mid-70s, which sort of goes under the name of the beta model. There were certain offshoots and children of the beta model which were more successful, and I'll touch upon those before finally sort of talking about a deterministic cascade model which you all can go home and play with. And there's particularly one interesting open question which I'll sort of, whoever's so motivated can go home and play with them. Okay, good. So that's okay. So what's the idea? The idea is one of the key ingredients in this cascade picture is that these daughter eddies are all space filling. So if you started with a volume of energy containing eddies V, at every stage, although you break them up into smaller sizes, they are space filling. Now, I know about intermittency. I know that my intermittent, anything which is sort of intermittent will have dead zones and alive zones. So I change this picture a little, and I say that this cascade will no longer be space filling. So I start with some scale L0, the large scale where I injected energy. That will give rise to a second generation of daughter eddies, but these daughter eddies will not be space filling. They will occupy a fraction beta of my original volume. Okay? And so on and so forth. So let me just check the notation n, because eventually I would like to change the notation that I use. Okay, so no, I have used R, so it's fine. Okay. Good. So what have I done? I've taken the space-filling cascade model, and I have introduced a new term, beta, such that at every generation, the fraction of volume which is occupied is beta times the previous generation. Is that statement clear, or? No, okay, let me try to recast it in a different language. Okay, so in the conventional cascade picture, which was consistent with Kolmogorov and which JKB had explained, that is the following. You start with big chunks of eddies of size L0, and then you say these over a characteristic time scale, which is L over VL or something. It sort of gives rise to daughter eddies, which are of size RL0, where R is a number between 0 and 1, but they're space filling. So if you calculate the volume of all the eddies here, it should be the same as the volume here. All right? And you continue to break it up like that till you reach the dissipative scale, and then energy dissipates. That was the picture. Now I demand that I don't want them to be space filling, but at each generation, I would demand that the fraction of volume occupied reduces by a factor beta compared to the previous generation. I don't change any other picture. So what I do is I make my model a bit intermittent, and I remove some of these daughter eddies. Yeah, so I'll come to that, because eventually I will try to derive these results from it. Okay? Why do I do what? Oh, why do I massage this? Yeah, so why do I massage the cascade picture? The reason I massage is, well, I didn't, Sulem and Frisch did, and others, is that by the 70s, it was clear that this picture was failing. This picture was failing. Mathematics wasn't working. So we needed a minimal model which might tell you why this picture is wrong. All right? That minimal model was motivated by the fact that experiments seem to show that there is intermittent structures in turbulence, that there are regions which are on and which are off. All right? So within this toy cartoon kind of picture, after all, it's sort of a bit removed from reality still, within this toy cartoon kind of picture, how do you incorporate the idea of intermittency? One easy way, the first way, eventually, it led to multifractals of the Mandelbrot variety, but one easy way was to say that when I create these new structures, I will make these new structures intermittent. You can do it randomly, but that's, when you start tackling a problem, you want to do the simplest way first. So the simplest way is you don't make these structures intermittent randomly at each generation, but you say that they go down by a fixed factor beta of the previous generation. That's all. Okay? Okay. Yeah, so the velocities change, and we will see how they change. So suppose this is a picture. Let's see where it leads us with all its limitations. So what this will lead us is a rather interesting result. So earlier, the fraction of these eddies which are so-called active was 1. That's because every generation it was volume conserving. Now, suppose you were here. In the next generation, your effective volume reduced by a factor beta, right? Over which, exciting things happen. I have gaps. You can see where it's leading, right? You can see it's leading to the fractal idea eventually. So you could, but I think the best way to think about it is that it's a nice sort of cartoon to have in one's. Oh, yeah, those I'm always very happy to think about. Yeah, exactly. So you can think Cantor set, you can think various stuff. Okay, so I'll just, because I'm running out of time, I can leave the holes for an exercise, but I can just do, yeah. So the fraction of space which is active after the nth generation will go as beta over n, right? Because at every generation, only beta survives of the previous volume, okay? Right? So now we know from the cascade model what is the typical size at the nth generation. The typical size at the nth generation is r to the power L naught. That was true for JKB's picture for Kolmogorov. All I've done is I have made some of these blobs inactive. I've turned them off. Okay? So using this in here, you can get a rather interesting result. Okay, good. Let me explain the result. I mean, getting the result is quite trivial. What it says is the following. So at nth generation, the fraction of my active volume is beta to the power n. Let's go it slowly. I mean, even if we don't do shell models, it's fine. But at least sort of some idea of the models. That statement is clear, right? I will sort of bootstrap myself a little later. So don't, I mean, for the moment, don't think about the, for the moment, just think about the geometric construction. Okay? Fine? So I know that L is r to the power n L0. That's how I construct my whole cascade picture. That's not everything that Kolmogorov taught me. And then I can use that and say the fraction of space which is occupied. And you know, if you do later courses in turbulence, etc., you will find this L0 appearing everywhere. It's an irritant, but it helps us. I can write down this. I can write down as L over L0, 3 minus d, where 3 minus d is defined as log beta over log r. Okay? Because I just made the substitution. Okay, everyone with me? I mean, हाँ उधर से ठीक है या हाँ चलिए I actually want to avoid a bit of self-similarity, but do it randomly. I mean, it's all right. I mean, you can do it randomly, deterministically. At this level of picture, it doesn't really matter. Okay? All I want to do is I want to shrink volumes by factors of beta at every generation. Right? It's like taking Cantor sets and removing 1/3 factors everywhere. Okay, good. The reason I write log beta over log r as 3 minus d is because it immediately gives me a sense of dimension. Think of a problem, okay, just to give a notion of dimension, think of the following problem. Take a 3D box. Okay, take a 3D cubic box. I mean, just to fix our ideas of dimensions a little. Take a 3D cubic box, draw a curve on it, okay? Have a surface on it. I mean, this is a standard textbook problems of codimensions. Draw a surface on it or have a point here. Now, suppose I want to draw a sphere in this cube of radius L. How would the probability of that sphere intersecting either the surface or the point or the curve be? I mean, this is a good way to understand how these dimensions, or what is my motivation in writing log beta over log r in terms of codimensions. Yeah, so what's this thing? In the analogous case, you would see that the probability of either the surface here or this curve or this point being embedded in a ball of radius L will go as L 3 minus d. Right? Was the question clear, or should I just reformulate it? So the question is the following. I have a cubic box, all right? In this cubic box, suppose I have a single curve inside, okay? Or I have a flat plane inside, or I have a point inside. Sort of a warning, I think. All right, so the question is, if I draw a sphere of radius L, what's the probability that it will intersect either the surface or the curve or the point? So think about this question, and then that would sort of give you a flavor of where this codimension ideas come from. I mean, since one was interested where these ideas come from, so that I don't know what was in the mind of the people who wrote down this model, but this is certainly a way to appreciate codimension. Okay, good. So what do we have? So what we saw that the energy over a scale L will roughly go as v squared over that scale L, right? Now, if at my scale L, I have a sort of fraction of occupation, which is PL, in the earlier case, it used to be 1. So now I multiply by a factor of PL. Is that reasonable for everyone? Okay. I can all right. So similarly, I can construct all, so for the velocity scale, exactly same ideas. I just sort of, for brevity, I'm just giving you the results without going through it, going through the steps of the algebra. Just use the same idea and the scaling arguments that were done in class before for the pure cascade model. For the velocity scaling, earlier we had VL, which went as L over 1/3, or R over 1/3. Now with this simple modification where I'm introducing a certain intermittency factor, where the cascade is not completely space filling, I immediately come up with a correction to my scaling. I was after corrections to scaling, right? So I immediately end up with not only having 1/3, but a correction of 3 minus d over 3. If d is equal to 3, then I recover Kolmogorov results. And what does d not equal to 3 means? It means that somehow my cascade is happening or is accumulating in sets of a dimension different from the space dimension. Is this picture completely confusing, or is there some hope to sort of address the confusion? So maybe now is a sort of good time to address the confusion. After that, things will be, I promise I'll go into lands which are less interesting, but more tractable. That's not a complete, when you make that statement, what sort of volume do you have in mind? Do you have in mind that a fluid which is being stirred in a box and it's not going to every part of the box, or do you have? Oh, well, okay. So in this case, what d not equal to 3 really means is the following. Look at here. What happens if you put d equal to 3 here? So the left-hand side becomes 0. So what it really means is if it was d equal to 3, that was the Kolmogorov kind of scenario, then your cascade would be space filling. So it is dimension in the sense of the dimension on which the cascade is happening. So it's not really a space dimension, which is why people are careful to write it in terms of this codimension form. So basically, you can actually go a bit further. What you can say is, as this cascade proceeds, it sort of accumulates on a set. What is the dimension of that set? That's probably the most sort of the most correct way of making that statement. I'll probably try to come back to you because I don't think I've convinced you, so I'll try to recast it in a different language. Yes. Again, exactly. Oh, so you're talking about the third order structure function, yes. So from here, you can actually construct the, so sorry, I didn't complete the story here, thanks. So let me write down what the exponent would look like using this. Again, the derivation, so probably there's some scan notes which are kept, right? So the derivations, I'll leave it on the scan notes because sort of, I don't want that. I can do this. Okay, the last stage. Yeah, so all I've done is I have massaged exactly whatever JKB was doing to get those scaling results, except that I've put in factors of PLs at the relevant places. Because now all the activity is happening not with probability 1, but with a certain probability of those animals actually being alive or not. Okay, all right. So, good. So Sanjib's question was, is the Holy Grail recovered, which is the third order structure function? Now from there, it's sort of trivial to construct what the scaling exponent looks like. It's trivial, but I still need my notes. So that's the third order, that's the scaling exponent. You have Kolmogorov's P third, wonderful. You have the correction to the Kolmogorov scaling as is seen in experiments. How far does that exponent agree with experiments? A bit, not massively. For 2 it is correct, for 3, 3 it is correct, but I mean, I don't have a tremendously great feeling why it comes out to be correct for p equal to 3, apart from the algebra. It's a convex function, so it can't be the Kolmogorov result, right? Oh, this result? It goes through these points reasonably well up to p equal to 4 or 5. However, and then I switch tracks and show that a lot of this is actually seen in controlled experiments using our computers. So point is that this is not where the story ends. This was in the early 70s when they came up with this beautiful beta model to find corrections to Kolmogorov to address issues of intermittency within the theoretical framework they had. Now, just remember historically, this is when Mandelbrot's papers started appearing on fractals and multifractals. All right? So this picture was then changed to introduce what is known as a bifractal model. What is a bifractal model? It's reasonably simpler, just like the beta model, except here you have 2 dimensions, D1 and D2. So there's a probability either you accumulate in a fractal set of D1 dimension or a fractal set of D2 dimension. And that gives rise to bifractality, which explains Berger's results beautifully. R has disappeared. So what I have is, yeah, so I have, and these are fitting. I mean, you can fit them around. You call them beta 1, beta 2, and you fiddle around with them. So in that sense, this exponent is not universal. There's a degree of massaging for the codimension. What one typically used to do is to take experimental data, mid-70s, look at this, figure out what the codimension is, and says, okay, fantastic, turbulence, this is my codimension. Fixing it? No. There is a more sophisticated way, but that's not what I'm going to talk about, which is, so let me just go step by step, Sanjib, that will sort of answer your question. So now you can say, why should, so, okay, when the dust has settled, what has this told us physically? What this has told us is one can be creative, imaginative, come up with a cascade model, introduce intermittency by hand, stop answering questions about what are these eddies and pretend that those questions are not good enough, and you come up and construct this model. And then this model gives you a prediction for the scaling exponent. Importantly, it gives you a prediction for h, which is your scaling exponent, and it says that in turbulence, my energy cascades or dissipation is happening on a fractal set with a single scaling exponent h given by this. All right? Now, yes. It is linear in P. Yeah, it sort of agrees up to a little within error bars. But remember in 70s, the error bars were quite large. Yeah. So you will get a nonlinear P in a second. Yeah. So there are sort of corrections which tend to reasonably fit here. I mean, 3 points, okay. Astrophysical. So now the question is, can you massage this model even better to make it A, more exotic, B, more precise? So the question is, you take the beta model, and this I won't go through because my mandate was to teach something called shell model, but that can be done in 10 minutes. That you can go through this exercise and say that my cascade is not accumulating on a single set, but it's accumulating on a multi-set, each of which has its own scaling exponent, and then you find what minimizes the scaling, and you pick out your, but those all involve a certain fitting parameter. And they eventually led to the mid-80s, what's sort of known as the Parisi-Frisch multifractal model. But the start is this, and so if you sort of vaguely follow what's happening here, you can go ahead and do the full multifractal, or you could meet me and we could do it together. Okay, fine. So just in the last 10 minutes, what the question was, all right. So we have, what JKB and I have sort of stressed is that most of the stuff in 3D Navier-Stokes is not understood. Frighteningly enough, we still travel on planes, but that's because engineers do a good job of actually simulating these flows, where, given our good computers and everything, we understand a lot through simulations. So far, we haven't gone beyond the 2-point correlation functions. We have tried to convince you that there is an energy spectrum going as k minus 5/3 and a scaling p by 3. Then I come and upset the apple cart by saying, okay, p by 3 is not the right one. What you see is something which is nonlinear. As a severe implication of that nonlinearity, even k minus 5/3 is not entirely correct. There is a certain correction to that 5/3. If there's a correction here, there will be a correction there. Wonderful. Okay, is there any way that one can see this without buying a wind tunnel or putting up a wind tunnel in your back garden, or without doing a lot of numerical simulations? Now, everyone has told you, especially those of us who do turbulence just to sound impressive, that numerical simulations are very hard to do in Navier-Stokes, and that's partly correct. Theoretically, you understand that. If you remember, JKB had derived this ratio of scales where it goes as Reynolds to the power 3/4. So the number of degrees of freedom will go as Reynolds to the power 9/4 in a cubic, this thing. Okay? So it's hard business. However, my take-home message here is there is a simplified model which works for reasons we sort of know and don't know, which you can actually simulate the people who are not going to Belur Halebit tomorrow. It will take you sort of half an hour to do it. Okay, let me write down that model for you, and then we are sort of done. So there was a homework assignment that JKB gave yesterday, which was to eliminate pressure from the Navier-Stokes equation using the Poisson equation. So I'm guessing that all of you have done that. In case you have done that, then you would know that the Navier-Stokes in Fourier space can essentially be written. Okay, those who have done that, just let me know if I'm messing it up. All right, so I may have messed up some indices, but this was your homework, so I'm sure you all have got it right in your, that was the homework, right? Jacobi, to get this? Okay, good. So you all would have the indices right. Let me just still check. So I have a UI here with K. Okay, so I can put this here. So that's compressibility. Okay, sort of fine. Good. Now the question is, this is the equation one would like to simulate, or the Navier-Stokes. And that becomes very difficult, and people have convinced you that it's difficult. Good. So people convince you it's difficult, especially who work on it, because that makes all of us look quite nice. All right. However, there is a simpler model which will essentially show you that some of these cascade ideas are not as outrageous as they seem to be, which is a class of models called the shell model. All right? So we stopped at beta, but we'll use the cascade idea. What is a shell model? So now I will run into a bit of difficulty, and I will try to hoodwink myself out of it. It's the following. Even if you haven't done this, the exercise, think about the Navier-Stokes in physical space. One of the things which hits you is that the nonlinearity. Okay, what am I after? What I'm after is I don't want to do a direct numerical simulation of this equation because it is hard. I want a simplified model which retains the virtues of the Navier-Stokes equation and which will give me the right answers, at least up to the 2-point correlation function level. That's my idea. All right. So now, in the Navier-Stokes equation, the nonlinear term is a wicked convolution. Right? What a wicked convolution, because all scales are coupled to each other, and that makes life hard for me. So I will make a statement which I hope will go uncontested, but it's worth contesting. What I will say is that although the nonlinear term makes everything reasonably non-local, I mean, all scales are mixed up with each other. That's what all this sweeping, etc. people talk about. I will say that in spite of that, the most important interactions are sort of local. So they happen between wave vectors of similar magnitude. Okay? This is a statement which can be hardened a little, but we really don't have time to go into that. I would strongly advise, for example, if you look at the Burger's equation, which is 1D, I think you can discover for yourself using dominant balance sort of ideas why that sort of happens. Okay, good. So I want to write a minimal model for this. First thing, what do? I want to write a minimal model for homogeneous isotropic turbulence. Okay, very good. So I get rid of vectors. All right? I construct a perverse Fourier space which is labeled by this index n. That's called my shell label. This perverse Fourier space is such that my Fourier wave numbers are logarithmically spaced. Why do I need to do that? I will come back a little later. It has to do with Reynolds number. Okay. So what do? I need to construct a simple scalar model which has all the great essentials of the Navier-Stokes equation in spectral space. What are the essentials? One is that I should have a dissipation which is something of this form. All right? I should have a nonlinear interaction which is roughly of this form. And I should have my equation which obeys the right conservation laws of the Navier-Stokes equation. Okay, so, right, good. So I begin my exercise in trying to do that. Homogeneous, isotropic, etc. I don't have big enough computers, vectors out of the window. I construct a weird Fourier space labeled by the index n. So it's a logarithmically spaced Fourier shell, okay? It's a scalar variable k. The eyebrows will go worse, Abhishek, as I reduce this picture dramatically. Okay. All right, so this is my scalar Fourier space, vector nature out of the window. Very good. With each of these in this, each of these wave numbers, I had a vector u variable. I take a scalar u variable labeled by n. That's my dynamical variable, the surrogate of u. Actually, eventually I will make it complex, but let's not worry about that. That has to do with phase space issues, but numerical phase space kind of things. Good. So I associate a un with this. So far, so good. U is associated with k. K I write as surrogate, kn, and I label u's with it. I look at this, and I want to write down an equation mimicking that. This term is no problem. If you accept this, then this you must accept without blaming me. All right? This term, if you accept this, is easy to do, right? It's just minus nu okay, so far so good. What about the nonlinearity? The nonlinearity is quadratic in nature, so I would A, require a nonlinearity which is quadratic in the u variables, and B, after all, I want to get some advantage. What advantage do I want to get? I want to say that here all scales are coupled. I believe in locality and God, so I would say that I will truncate my interactions to just nearest and next nearest neighbor shells. I'm allowed to do that. I mean, I could ask for permission to do that, so I do that. So plus a nonlinear term, which is quadratic and nearest and next nearest neighbor interaction. So let me see what that term looks like. I mean, the actual. Maybe I should rather write the final results and then this thing. Okay. So the nonlinear term this is my nonlinear term. Did I know this beforehand? No, I did not. I wrote down various combinations of possible, for the nth shell, quadratic combinations which includes nearest and next nearest neighbor shells. Okay, that's what I set out to do. Having written, yeah, Sanjib, yeah. Stopping at the nearest makes a problem in phase space conservation, so I'll come to that in a second. I mean, there were people who stopped it in the 70s, Novikov, Stewart, the Russian gang, and yeah. Next nearest neighbor was introduced after, and then they all made these variables complex, but that's the correction. Let's not, you know. One uncharitable school is that, okay, you are very finicky about looking in Fourier spaces complex, so why not make it complex? But there's a more compelling reason to make it complex than aesthetics or, you know, to be like the Jones. Okay, This is my nonlinear term. Could I have had other terms? Of course I could. There were various other couplings which involve nearest and next nearest neighbor terms. Why do I stop here? And can I determine these A, B, and C's? That's the idea. This I've worked out in the notes which Abhishek will put up, but let me tell you the spirit of it because it's touching 4. The spirit of it is the following. You look at the Navier-Stokes, so this is a shell model, full stop. This logarithmically spaced, typically you use 22 shells or etc. In today's computer, you can get all 2-point results in turbulence, including all these exponents accurately, correctly within half an hour of writing the code. Okay, so it's a bunch of ODEs. So the PDE has been replaced by ODEs. Okay, 45 minutes. Okay, how do I go about it? How do I solve for this? Or how do I know these interactions? For this, you go back to the original Navier-Stokes equation. So here, you're fudging and sometimes not fudging. You want your minimal model to at least respect the invariances of the actual Navier-Stokes equation. What are the invariances? That's precisely what JKB was discussing today before lunch. So, you know, in 3 dimensions, there's energy, there's helicity. We probably didn't do helicity. Okay, so there are certain invariances in 3D. In 2D, there's the entropy and the kinetic energy. So you fix A, B, and C's by using those conservation laws. In the limit, in the case where viscosity is 0 and there's no forcing, you can put a force if you want, by the way, then this system must conserve whatever needs to be conserved for whichever dimension you're looking at. Amazingly enough, if you use 2D conservation laws, they'll give you the dual cascade. You'll get all the energy and entropy cascades that JKB was talking about. If you use the 3D invariance, this guy will give you all these nice pictures, all the distribution functions, all the exponents, the Kolmogorov scaling, and everything. What it lacks is there's no real space structure to this equation. People have attempted a real space version of this using a sort of strange Fourier transform, but you know, yeah, okay. But okay, people can claim they can do it, but I'm not sure if they can. Okay, once you fix, and there's a third very interesting constraint on the Navier-Stokes equation, which I think JKB did not touch upon at all, is that in the case of vanishing viscosity, there's a phase space conservation. So Sanjib, if you allowed for only nearest neighbor and yet retain the quadratic nonlinearity, you would get into trouble trying to impose phase space conservation. This beautifully does it. So once the dust settles, so there are sort of various sort of, the most popular one is known as the Goy shell model, named after Gledser, who in the 80s wrote down exactly this equation. And Okitani and Yamada solved it numerically and found that it gives rise to chaotic solutions. Then there's another variety called the Sabra shell model. Strongly encouraged to read up about both. It has a very interesting, if not a bloodied history. And once you do that, you end up getting really very easy to write down this equation and solve it numerically. Just keep in mind it's a sort of stiff differential equation, so be careful with the time stepping. And you can reproduce all the results, which made a lot of people correctly, you know, significant players in the growth of understanding turbulence. Are there any open questions? Why should you want to write about it? It's a good tool to play with. There are lots of models where you can still apply it and, you know, do a lot of very good job about it. The only question that I would like to leave you with is because neither of us touched on the mathematics of Navier-Stokes, so let me sort of intrigue you a little. What is, so that's a question if any of you write down the shell model, what is the functional form of the spectrum in the dissipation range in a shell model? In the actual Navier-Stokes, it's exponential for reasons which we can discuss outside, I'm here. In the shell model, is it different? Then it tells us something more, which I'll be very happy to discuss, but it's, yeah.